Welcome back to the AI Research Roundup. I'm your host, Alex, and today is May 5th, 2025. Okay, so today we're looking at an interesting ICLR conference paper called Reasoning Elicitation in Language Models via Counterfactual Feedback, published back in late January, about 3.5 months ago. This paper digs into how large language models, or LLMs, struggle with causal reasoning, particularly counterfactual, what-if questions, revealing a gap between recall and real reasoning. Okay, so this figure right here really drives home that point about the reasoning recall gap. It shows the error rate for the Phi-3 mini model on a math problem, asking about divisibility by 6. You can see the model makes far more errors on the counterfactual what-if version compared to the straightforward factual question. It really highlights how much harder genuine causal reasoning is for these models compared to just recalling facts. Okay, so building on that reasoning gap, this figure shows how the researchers tested generalization. It defines 4 modes: common cause, common effect, inductive, and deductive. You see the blue dashed lines. That's the kind of causal relationship the model was trained on. The orange lines then show the related, but different, causal links they actually tested it on. Well, it's about seeing if the improved reasoning transfers beyond just the specific training examples. Alright, so this next figure really gets into why the researchers felt they needed new metrics beyond just simple error rates. It contrasts causal consistency with correctness. See, you can have the same average error rate, but the underlying pattern of errors, like whether they relate to necessity or sufficiency, can be very different. This really shows that just measuring factual and counterfactual correctness doesn't tell the whole story about the model's causal understanding. So, to tackle that consistency problem we just talked about, this figure lays out the different fine-tuning methods the researchers explored. It shows standard supervised and preference-based approaches using counterfactual feedback, but the key innovation is the third one, preference-based causal consistency feedback, or CCF. This method directly addresses consistency by using paired factual and counterfactual questions in the same dialogue, explicitly training the model to align those answers causally. Okay, so moving to the results. This figure plots the performance of those different tuning methods we just discussed, specifically on an in-domain puzzle task. It charts sufficiency inconsistency rate, SIR, against factual and counterfactual errors. Notice how the methods using both factual and counterfactual data, particularly the DPO plus CCF approach in green, end up in that desirable bottom left corner, achieving low errors and, critically, much lower sufficiency inconsistency compared to the others. Okay, so while the previous figure focused on in-domain results, this table broadens the view to generalization across 3 real-world causal reasoning problems. It shows the average error rate and that average inconsistency rate normalized against the base model. Well, we see that using both factual and counterfactual data, especially the DPO plus CCF method, generally reduces errors and inconsistency compared to the base. Inductive generalization looks particularly strong, but some modes, like common cause, show less improvement, especially for consistency. Alright, so wrapping things up based on those generalization results, the main takeaway here is that really improving causal reasoning in these models needs feedback incorporating both factual and counterfactual information. Specifically, that causal consistency feedback approach looks like a really promising way forward, particularly for getting that reasoning to generalize inductively. Okay, that's all for this AI Research Roundup. Thanks for tuning in.